Hi, welcome to Lesson 4.2, Straight Line Motion, Connecting Position, Velocity, and Acceleration. This is Topic 4.2 from the 2019 course and exam description for AP Calculus AB. Now, let's take a look at our instructional framework. Our instructional objective is that students will be able to calculate rates of change in order to solve rectilinear motion problems involving position, speed, velocity, and acceleration. Our inquiry question is, how can we use derivatives to solve real-world problems involving rates of change? Our standard is CHA3B1. The derivative can be used to solve rectilinear motion problems involving position, speed, velocity, and acceleration. Take a moment and think about how this standard could be assessed on the AP Calculus test. We have already dealt with position, velocity, and acceleration in Unit 2, but here we concentrate on one-dimensional motion, either horizontally on the x-axis or vertically on the y-axis, such as a falling body. Note that the motion in this case is confined to an axis and not the graph of the function. In this lesson, remember that s of t, x of t, and y of t are functions that give the position of a particle at time t. The change in position, delta s, is called displacement, and so average velocity is the displacement divided by elapsed time. This is equivalent to the average rate of change formula applied to position. Note that this is the slope of a secant line. Instantaneous velocity is the first derivative of the position function. This is the instantaneous rate of change applied to position, and it gives the slope of the tangent line. Remember that velocity is a vector quantity. It has both magnitude and direction. But because we're working only in one dimension, we are able to represent both characteristics with a signed value. The unsigned value, the absolute value of velocity, is the speed. Acceleration is the instantaneous rate of change of the velocity function. This means that it is the first derivative of velocity and the second derivative of position. Finally, displacement over an interval of time, AB, is the difference in values SB minus SA. Distance traveled is different than displacement. I can pace back and forth for 10 minutes and return to my starting location. My displacement would be 0, but my Fitbit would give me distance traveled. To find this from a graph, we simply add up all of the absolute values of distances between turning points. Objects in freefall will have motion governed by the equation s of t equals negative 1/2 gt squared plus v naught t plus s naught. Here, g is the gravitational constant, which is the acceleration due to gravity. Different planets have different gravitational constants, but on Earth, g is equal to 9.8 meters per second squared, or 32 feet per second squared. Finally, when velocity changes sign, either from positive to negative or from negative to positive, this indicates that the particle has changed directions. The focus of this lesson is to make connections and transition between position, velocity, and acceleration functions as they relate to the skills and rigor on the AP Calculus exam. In this lesson, we will look at algebraic and numerical problems, table problems, and graphical interpretations related to straight line motion. In example 1, we are told that a particle moves along the x-axis so that any time t greater than or equal to 0, the position is given by the function x of t equals t cubed minus 9/2 t squared minus 12t plus 5. In part A, we're told that at t equals 0, we need to determine whether the particle is moving to the right or to the left, and then explain how we know. So they want us to determine whether the particle is moving right or left. and they want us to find out what's happening specifically when time t is equal to 0. Well, to determine the direction of the particle, we need to find the velocity function, because remember, if the velocity is positive, it's moving to the right. If it's negative, it's moving to the left. So let's find out what v of t is. So v of t is equal to x prime of t, and then applying the power rule, here we have 3t squared minus 9/2 t squared. If we take the derivative of that, 2 times 9/2, the 2's cancel and we get minus 9t, and then minus 12. So here's my velocity function, 3t squared minus 9t minus 12. Now let's find the velocity at time t equals 0. So v of 0 is equal to, and if we substitute 0 for t, these two terms go to 0, and we're just left with negative 12. Okay, so now we know that the particle is moving left, but we have to give a reason for this. So because v of 0 equals negative 12, v of 0 is less than 0. It's negative. So since the velocity is negative, it's moving left. In part B, they ask us at what time or times does the particle change direction? Justify your answer. Well, if the particle is changing direction, going from left to right or from right to left, that means that the velocity is changing sign from either negative to positive or positive to negative. So let's start by finding where the velocity could be equal to 0. That would signal a sign change. So remember our velocity function, we just found that in part A. It's 3t squared minus 9t and then minus 12. And so we'll set this equal to 0, and now we can solve for time. So factoring out a 3, we have t squared minus 3t minus 4 equals 0. And if we multiply through this equation by 1/3 or divide through by 3, we can eliminate the 3. And then we can factor t squared minus 3t minus 4. Well, okay, so positive 1 and negative 4. Positive 1 times negative 4 would give us negative 4. Positive 1 plus negative 4 gives us negative 3. So let's do t plus 1 times t minus 4 equals 0. Then the 0 product law, we set each of these factors equal to 0 and solve. Okay, and over here we get t equals negative 1. Well, that's a mathematical solution, but it's outside the interval for our physical problem. In this problem, our time is starting at t equals 0, so this is not a valid solution. So we have t equals 4 seconds, and so this would indicate a possible sign change for velocity. So let's see if we can bolster our argument by determining whether or not it actually did change directions. So just because a quadratic equation is equal to 0, that doesn't necessarily mean that it is changing sign. It could be that it is the vertex of the parabola just touching the x-axis, in which case there would be no sign change. But since we had two roots, it stands to reason that we're going to have a sign change here. But let's find out what direction it's changing from and to. And to do that, we can just plug in some values on either side of 4 seconds. So for instance, let's find out what v of 3 is. And then v of 4, we've already found, is equal to 0. And then v of 5. And so if you have your calculator, you can do this very quickly. Just substitute in 3 into your velocity function, and we should get negative 12. And then if we substitute 5 into the velocity function and find v of 5, we should get 18. And so here we can see that at time t equals 4, the velocity changes from negative to positive. So now I think we are ready to provide an explanation. So particle changes direction from, so this is negative velocity. So it starts out, it's going left. So from left to positive velocity right, since v of t changes from negative to positive at t equals 4 seconds. Now let's take a look at part C. At t equals 1, is the velocity of the particle increasing or decreasing? Explain your answer. Well, think about what it means for velocity to be increasing or decreasing. If the velocity is increasing, that means that there is a positive acceleration. If the velocity is decreasing, that's a negative acceleration. So to answer this question, all we really need to do is to find out the sign of the acceleration at time t equals 1. Let's start by finding the acceleration function. So I'm going to write a of t is equal to v prime of t. And so we need to take the first derivative of our velocity function. So using the power rule, 2 times 3 is 6t. Minus 9. So now let's find the acceleration at time t equals 1. So a of 1 is going to be 6 times 1 minus 9. Well, that's negative 3. So there's our answer. The acceleration is negative, so that means the velocity is decreasing. Let's write that up, and we have to justify our solution by referring to our work. So let's see. So the particle's velocity is decreasing at t equals 1, and so we have to give a because a of 1 equals negative 3, so a of 1 is negative. Now let's look at part D. At t equals 1, is the speed of the particle increasing or decreasing? Justify. Well, at first glance, it almost seems like we just answered this question, in part C. But remember, there's a difference between speed and velocity. So what does it mean for the speed to be increasing? Well, so the speed is the absolute value of the velocity. So imagine we have an object that is traveling to the right. The acceleration can be thought of as like a push. Now, if the object is traveling to the right and we push it to the right, its speed is going to increase. But if the object is moving to the right, it has a positive velocity, and we push it to the left, it has a negative acceleration, the speed is going to decrease. It's going to slow down. So what we're looking for here are times when the velocity and the acceleration have the same sign. So let's begin by finding the velocity at time t equals 1 second. So that's going to be 3 times 1 squared minus 9 times 1 minus 12. And so that's going to give us a value of negative 18. Now, a of 1 is equal to 6 times 1 minus 9, which is negative 3. And you'll notice that we have the same sign for our velocity and acceleration. And what that means is the speed will be increasing. Let's make an argument. So since a of 1 is less than 0 and v of 1 is less than 0, both have the same sign at t equals 1, so particle's speed is increasing t equals 1. Now let's look at part E. What is the particle's acceleration at t equals 1/4? Explain the meaning of your answer in terms of the particle's velocity. How would units be explained in context to the particle? Okay, well, a of 1/4 is equal to 6 times 1/4 minus 9, which is equal to 3 halves minus 18 halves, or negative 15 halves. Now, what does this mean in terms of the particle's velocity? So this means that the particle's velocity is decreasing at t equals 1/4. Why? Because the acceleration is negative. Notice we're talking about velocity. We're not talking about speed, so we don't need to worry about them being the same sign or different signs. For velocity, it's a lot simpler to think about. If the acceleration is negative, then the velocity is decreasing. Now let's talk about units. So we have negative 15, distance over time. Since acceleration is the rate of change of the velocity. It's the change in the velocity per unit time. So this would be a change of negative 15 meters per second every 2 seconds. So this actually simplifies to negative 15 over 2, and the units here would be distance over time squared. Now let's look at example 2. In this example, our information is presented in table form. So the table below gives the velocity in feet per second of a particle moving along a horizontal axis. The velocity v is a twice differentiable function of time t. So we have time in seconds, velocity in feet per second. Let's look at part A. At t equals 0, determine whether the particle is moving to the right or to the left. Explain how you know. Well, remember that velocity is assigned value. And so if velocity is negative, we're moving to the left. If it's positive, we're moving to the right. If velocity is equal to 0, then we're sitting still. So let's see what the velocity is at time t equals 0. So v of 0 is equal to, and from our table we can see that it's negative 4, and I'm going to write my units. It's feet per second. Okay, well, that's less than 0. That's negative. So at this point I think I can make an argument. At t equals 0, the particle is moving left at a rate of 4 feet per second because v of 0 is negative. Part B, is there any time or times during the interval from 0 to 15 seconds when the particle is at rest? Explain your answer. So in other words, when is the velocity equal to 0? Well, we can really just jump right into answering this, but we need to be very careful. And the reason is we're going to use the intermediate value theorem, and we want to make sure that we are providing a cogent argument for its application. Now, if you look at this table, you can see that we go from negative values to positive values. And so the idea is that there's going to be a time when the velocity is equal to 0 between t equals 2 and t equals 3 seconds. The velocity has to go through 0 on that subinterval. But in order to use the intermediate value theorem to make this argument, I first have to know that it's a continuous function. Well, remember that in the directions they told me that the velocity v is a twice differentiable function of time t. And so what that means, if it's twice differentiable, that means that it's differentiable. So v of t is differentiable. And if a function is differentiable, it has to be continuous. So we've met that requirement for the intermediate value theorem. Now let's make our argument based on the table. V of 2 is negative 1, V of 3 is positive 1. So therefore, by the IVT, there exists a time between 2 and 3 such that V of t equals 0 and particle is at rest. Moving on to part C, use the data from the table to find an approximation for v prime of 8. Explain the meaning of v prime of 8 in terms of the particle's motion. Show the computations that lead to your answer and indicate the units of measure. Okay, so we're looking for v prime of 8. And we're told we're going to find an approximation for this. Well, first of all, what is v prime? V prime is acceleration. It's the rate of change of the velocity. And the reason I have to find an approximation is that I cannot find the instantaneous rate of change. I can't because I don't have the velocity function in order to take the derivative. Since they gave me the function in table form, what I'm going to have to do is look at a subinterval that contains 8 seconds and use that to calculate an average rate of change. So I'm going to use these values here. From 7 to 10, the velocity changes from 3 to 5. So let's find the average rate of change over that subinterval. So the first thing I need to show is that 8 is on this subinterval from 7 to 10. And now we can find the average rate of change, v prime of 8 is equal to v of 10 minus v of 7 divided by 10 minus 7. Now, v of 10 was 5, v of 7 was 3. 5 minus 3 over 10 minus 7, and we have 2 over 3. And our units are going to be feet per second squared. Okay, so let's write up our conclusion. So at t equals 8 seconds, particle's velocity increasing from 7 feet per second to 10 feet per second. All right, let's look at part D. Find the average acceleration of the particle for the interval from time t equals 10 to 12 seconds. Explain what this number means in terms of the particle's velocity on the interval. So the average acceleration is going to be another average rate of change. But remember that acceleration is the rate of change of velocity. And so we're looking at the average rate of change of the velocity from 10 seconds to 12 seconds. So average acceleration is equal to v12 minus v10 divided by 12 minus 10. And so let's see what these values are. We'll go back to our table. V of 12 is 3. V of 10 is 5. So we have 3 minus 5 over 12 minus 10. 3 minus 5 is negative 2. 12 minus 10 is 2. So that's negative 1. And the units are going to be feet per second squared since it's an acceleration. So let's write up our interpretation of this. Average acceleration over this interval means that the velocity was decreasing. Why? Because the sign was negative. On average, at a rate of 1 foot per second. And let's look at part E. Let A of t equal v prime of t. Is there a time t equals c guaranteed such that A of c equals 0 in the interval from 0 to 15? Justify your answer. Okay, so this is a mean value theorem problem. So we're looking for the derivative of velocity being equal to its average rate of change. The first argument that I need to make is that this derivative is continuous. Well, since velocity is differentiable, remember that differentiability implies continuity, but it doesn't work the other way around. So because v of t is differentiable, they told me that in the problem, on the interval, that means that acceleration is continuous. Now let's go to our table and think about what this means. So we're looking for a time t equals c where the acceleration is 0. Let's look at the table. So what is the velocity doing here on this interval? Well, the velocity starts at negative 4, and then it's negative 1, so it's increasing. From negative 1 to 1 was an increase. From 1 to 2 was an increase. From 2 to 3 was an increase. From 3 to 5 was an increase. But then at 12 seconds, I'm back down to 3. And so I'm decreasing. What does that mean about the acceleration? Well, the acceleration is positive, and then the acceleration becomes negative. I start slowing down from 5 to 3. So that means that from 7 to 10, the acceleration was positive, and from 5 to 3, the acceleration was negative. At some point between 7 and 12, there had to be a point where the acceleration was equal to 0. That's what the mean value theorem says. So let's look at these individual subintervals from 7 to 10 and from 10 to 12. So v of 10 minus v of 7 over 10 minus 7 is equal to 2/3, which is positive. Also, v of 12 minus v of 10 over 12 minus 10 gives us negative 1, which is negative. And so here's our argument. Thus, a of t equals 0 on 7 less than t less than 12 seconds. So far we have considered algebraic and tabular representations of motion functions, and now we consider a graphical representation. So here we have velocity on the y-axis and we have time on the x-axis. Now it's important to remember that this is not a graph of position, so this does not show us the path taken by the particle. This is a graph of velocity. Remember, the particle is confined to, say, the x-axis. So let's take a look at example 3. The graph below is y equals v of t, the velocity of an object moving on a line over the time interval from 0 to 10 inclusive. Assume that the positive direction is to the right. In part A, they ask, on what interval of time is the object moving to the right? Let's look back at the graph. So the object will be moving to the right whenever the velocity is positive. And we can see from the graph that the velocity is above the x-axis. It's positive between 4 seconds and 10 seconds. So we'll indicate our criteria where v of t is greater than 0. So on the interval from 4 to 10, notice that the 4 and 10 are not included. I didn't put less than or equal to, I just put strictly less than. And the reason is because at 4 seconds the velocity is 0, and same at 10 seconds. So it doesn't have a positive velocity at those times. If you write it in interval notation, it would be 4, 10 in parentheses instead of square brackets. So that'll be when the object is moving to the right. Let's look at part B. In part B, they ask, when is the object speeding up? Now notice, they're asking about speed. They're not asking about velocity. And so to determine whether the speed is increasing, and this could happen in either the positive direction or the negative direction, we need to find where the velocity and the acceleration have the same sign. So let's look at our graph. If we look at the interval from 0 to 2, the velocity is negative. It's below the x-axis. But the acceleration is going to be 0 because the slope, the rate of change of velocity, is 0. The slope is a horizontal line. Between 2 and 4, the velocity is still negative, but now we have a positive acceleration. The slope is positive. So what that means is that here the object is actually slowing down. And the reason is because the velocity is negative and the acceleration is positive. They have opposite signs. But on 4 to 6, we can see that the velocity is positive. It's above the x-axis. And the slope is also positive. And so here we have a case where the particle or the object is speeding up because the velocity and acceleration have the same sign. Between 6 and 8, we're again traveling at a constant velocity. The slope is 0. The acceleration is 0. And then between 8 and 10, the velocity is positive, but the acceleration is negative. And so this would be an instance when the speed is decreasing, because the acceleration and the velocity have opposite signs. The only interval during which the velocity and the acceleration are both positive is from 4 to 6. So let's go back. So when is it going to be speeding up? Well, it's going to be speeding up when the velocity and acceleration have the same sign. So this happens on 4 less than t less than 6, where the velocity is positive and increasing. In other words, a of t is also positive. In part C, they ask, how fast is the object moving at time t equals 3, and in what direction? Let's take a look at our graph. Well, at time t equals 3, we can see that the velocity would be -5. So let's write v of 3 equals -5. So the speed is going to be the absolute value of the velocity at 3 seconds, which is just equal to 5. And they didn't give us any units here, but it would be distance over time. And since the velocity was negative, that means that it's going to be moving left in a negative direction. So by reducing velocity down to here's the speed and here's the direction, it forces us to decode the meaning of this integer. In part D, they ask, what is the average velocity over the time interval from 0 to 4 and from 4 to 10? And they want us to show our work. If I were doing this with an algebraic function, I would use the average rate of change formula. That would give me the total distance traveled divided by the duration of time. Problem is that they've given me a graph of velocity versus time. How do I get distance off of a graph like this? Well, think about what velocity is. Velocity is equal to distance over time. And if I solve this for distance, we get distance equals velocity times time. Now look at the graph just on the interval from 0 to 2. We're traveling at a constant velocity, -10, and we do that for 2 seconds. So if I multiply the velocity times time, that gives me an area bounded by the x-axis and these limiting values of 0 to 2. And this area is equal to -20, and that's going to be the distance traveled. Now here's a question. How do I find the area where the velocity is changing? Well, we know it's the area, so it's velocity times time. Why don't we just multiply using a formula for the area of this bounded region? So in this case it would be 1/2 base, which is 2, times height, which is -10. So half of -10 would be this midpoint here, -5 times 2, and that's going to give us -10. Let's go back. So for 0 less than t less than 4, distance traveled is going to be -20 plus -10 equals -30, and the time was equal to 4. So the average velocity is going to be -30 divided by 4, which is equal to -7.5. Let's do the same thing for the interval from 4 to 10. So from 4 to 10, we can divide this region up into 3 separate regions: a triangle, another triangle of the same size, and a rectangle. Okay, so let's do the easy one first. Between 6 and 8, we have a velocity of 15. So that's going to be 15 is the velocity times the time, which is 2 seconds. So this gives me a distance of +30. Here we can do our triangle formula. So we've got 10 minus 8 is 2. 2 times 15 is 30, and then half of that is going to be 15. So that means this region here is also +15. So from 0 to 10, our distance traveled is going to be 15 plus 30 plus 15 equals 60. And we traveled over a time of, that wasn't 0, that was supposed to be 4. Let me fix that. 10 minus 4 is 6. So the velocity, the average velocity, will be 60 divided by 6 is equal to +10. In part E, they ask, what is the total distance traveled by the object? Show the computations that lead to your answer. Well, you know, we've already found this negative distance and this positive distance. This was -30 and this was +60. Now remember, they're asking for the total distance traveled, not the displacement. And so that means that my Fitbit is going to be counting if I'm walking in a negative direction. So let me take the absolute value of these signed distances. And whatever the units of distance are, they weren't given in this problem. In part F, they ask, when is the object slowing down? Justify. Well, all right, this is the other version of our speed question that was asked earlier. Before they asked, when is it speeding up? And remember, we said that happens when the velocity and acceleration have the same sign. Well, when does it slow down? When velocity and acceleration have opposite times. Okay, so when does that happen? Let's look back at our graph. All right, so constant acceleration, that's 0. constant acceleration, that's 0. Here we have a negative velocity. It's below the x-axis, but the acceleration has a positive slope. So from 2 to 4, our velocity is negative, but acceleration positive. Let's see when else this happens. So from 8 to 10, we have a positive velocity and a negative acceleration. So in this case, the velocity was positive and decreasing. Put A is negative. Part G asks, when is the velocity increasing? Explain. So this is actually, at least for me, this is less complicated than speed. Velocity is increasing when the acceleration is positive. So here we have a positive acceleration from 2 to 4, again from 4 to 6, and those are the only positive slopes that I have on my velocity graph. So when A of t is greater than 0, velocity increases. This happens on 2 to 4 and on 4 to 6. Finally, part H, on what interval or intervals does the object move at a constant speed? Well, that was where the acceleration was 0, or where the slope of the velocity was equal to 0. So that was from 0 to 2 and from 6 to 8. Alright, next we'll look at example 4. Example 4 is the first of our calculator questions for this section. So here we have a velocity function, natural log of t minus 0.15 t cubed plus t squared plus 2t quantity to the 4/5 power. So let's go ahead and enter this expression into our calculator. So we'll go to y equals, and we'll type in natural log of x, close parentheses, minus 0.15 x cubed plus, open parentheses, x squared plus 2x, close parentheses, to the 4 divided by 5, and there's our velocity function. Let's go back and see what they want us to do. For t equals 4, is the object speeding up or slowing down? Justify. Well, we could just graph this and look at it from 0 to 6, but we can do it computationally also. So let me do this. If I want to answer a question about speed, remember that's going to be where the velocity and acceleration have the same sign. So let me find acceleration. Acceleration is the first derivative of the velocity. So how do I take a derivative on my calculator? So we'll go to y2, and we're going to let y2 be equal to, and I press math, and I go down to n derivative, so I press 8. And I'm taking the derivative with respect to x, and what I'm taking the derivative of is y1. And there are shortcuts on the new calculators, but on an old calculator you'll do vars, y-vars, function, y1, and then we're just going to let x equal x. And that way I can substitute any value I need in, but this will calculate the derivative. Let's go back to the main screen, and I want to find out what is v of 4 and what is a of 4. So let's find v of 4. Vars, y-vars, function y1, 4, enter, and we get 4.4969. Let's go to vars, y-vars, function y2, and let's plug in 4, and we get negative 2.71. So here's our analysis based on the calculator. V of 4 is approximately 4.49698. A of 4 is approximately negative 2.71310. And so we'll say, since V of 4 is positive and A of 4 is negative, opposite signs means the object is slowing down at time t equal 4. In part B, they ask at what time on the interval from 0 to 6 does the particle change directions. So remember that when the particle changes directions, that's when the velocity changes sign, either from negative to positive or from positive to negative. And so to find a sign change in velocity, the first thing I want to do is to find out where is the velocity equal to 0, because that signals a potential sign change. So I think actually in this case I do want to look at the graph. So let's do this. Let's go to window settings, and since we're on the interval from 0 to 6, we'll let xmin be 0 and xmax be 6. Our x scale is 1, and I'm not worried about the ymin and ymax because I have a negative and a positive value. I just want to see the x-axis, so that should definitely show up on our graph. Let's take a look. You'll notice here we have two functions, so the blue function and the red function. So let's remind ourselves about what's going on here. The blue one is our velocity. The red was the derivative of that. That's acceleration. So we don't really care about the red function, but if we look at the blue one, I do in fact have two x-intercepts. And so these are the points where velocity is equal to 0. I don't want to guess what these values are, and I also don't want to try to trace with my cursor, because that's just going to give me an imprecise approximation. Let's use the equation solver. So we'll go to second, trace. That takes us to the calculate menu, and we'll find the zeros of the function. So we'll do 2. Now I could scroll, but it takes a long time, and honestly on the AP exam you don't have time to spend scrolling across a function. So here's a shortcut. Just type in the values for your left bound and your right bound. And so for this x-intercept, I'm going to let 0 be my x bound and 1 be my right bound. So we'll just choose 0, and the right bound will be 1, and then just press enter, and here we have our 0.3911065, and you can see that velocity is going from negative to positive. So let's write this up. So v of t is equal to 0 at t is approximately 0.39109, and v of t changes from negative to positive. So the object changes direction from left to right. Okay, but that's just half of the story. Let's go back. We have another x-intercept here. So let's see, for this one I think we'll use t equals 4 as our left bound and t equals 6 as our right bound. So let's go to second, trace, 2, and left bound is going to be 4. So there it is, and then right bound is going to be 6. So there it is, and you just press enter. 5.00765008. So we'll say at t is approximately 5.007765, v of t equals 0, and v of t changes from positive to negative. So object changes direction from right to left, and that's it. In example 5, they tell us that a particle moves along the x-axis, so at any time t greater than 0, its velocity is given in meters per second by this function, 4 plus 2.3 sine 0.85 t. What's the acceleration at time t equals 4? And then they want us to interpret this in terms of the direction of the particle. Okay, this is a calculator problem, and again they're asking about acceleration, but remember that acceleration is the first derivative of velocity. So what we're looking for here is a of 4. Let's go to the calculator and let's put in our function. So we have 4 plus 2.3 sine 0.85x. Now that's our velocity function, and we're going to take the derivative of that. So we'll go to math, in derivative, so 8. Taking the derivative with respect to x of y1, so vars, y vars, function y1. And we're going to evaluate this at x equals 4. So just press 4, enter. Let's go back to our screen. So second quit, and we'll do vars, y vars, function y2, enter. negative 1.89009. So the effect of this acceleration on the particle, oh, you know what? Let me put some units in here. Meters per second squared. So what does this tell us about the direction of the particle? Well, as far as the acceleration is concerned, that just means that the particle is being pushed to the left at a rate of 1.890 meters per second squared. In example 6, they tell us an object moves along a line so that at time t, from 0 to pi, its position is given by s of t equals negative 3 sine 0.25 t squared plus 1. What is the velocity of the object when its acceleration is 0? And then describe the behavior of the object. Okay, so remember that the velocity is the derivative of our position, and acceleration is the derivative of velocity. So let's put this in our calculator and then start taking some derivatives. So we have negative 3 sine 0.25 x squared close parentheses plus 1. Now y2 is going to be my velocity. It's the derivative of position. So let's go to math 8. Derivative with respect to x of vars, y vars, function y1, and we'll just evaluate it at x to get a general derivative. Enter. And now let's take the derivative of this function. Math in derivative x vars, y vars, function y2, evaluated at x. Second, quit. And I want to graph these. So let's go to window, and remember the interval is 0 to pi. So I'm going to let x min be 0 and x max be pi. And let's think about the sine function. So the sine function, if it's negative 3, is going to go down to negative 3 and up to positive 3, but the whole graph has been shifted up 1. So we're going to be going from negative 2 to positive 4. So let's let our y min and y max be negative 3 to 5. So 0, pi. Let's let our x scale be pi over 4. So second pi divided by 4. Y min will do negative 3 to 5. Okay, so let's take a look at these functions. So the first one, the blue one, is position. The red one is velocity. The black one is acceleration. And if we look at our question, they want to know, what is the velocity when the acceleration is 0? So we've got to find when the acceleration is 0. So that's going to be the x-intercept of my acceleration graph. So we'll do second calc 0. And it selects my first function, but you can toggle using the up and down arrow keys. And so now I'm on y3, which is my acceleration. So just press enter since we're to the left of the intercept, and then here we are to the right of the intercept, and enter, and here's our 0, 1.6165. So a of t equals 0 at t is approximately 1.6165,038. And they want to know, what is the velocity at this point? So velocity of 1.6165 is approximately, and this is the cool thing about graphing all three of these on top of each other. I'm going to toggle through these graphs one more time using the up arrow key, and that drops me onto the next function, which this is my velocity function. This is y2. And so you can see I still have the same x value, but here's the y value, negative 1.925. So I don't even have to plug in to the velocity function and retype in this number. It's already calculated the corresponding y value for that function, and so I can just write that down. So let's say that a of t equals 0 at t is approximately 1.6165,038, and velocity of this value, 1.6165, is approximately negative 1.92549 8. So the object is moving to the left at t is approximately 1.617 when the acceleration equal to 0. In example 7, we've got one last calculator problem. They tell us a particle moves along the x-axis, so on the interval from 0 to 15, velocity is given by the function tangent of cube root of t minus 0.2 t. In part A, they want us to find the time t when the acceleration is 0, and then interpret what this means about the velocity at that time. Well, remember that the acceleration is the derivative of velocity. So let's put this function in our calculator and take the derivative. So we'll go to y equals, and we have, making sure we're in radians, we have tangent x to the 1/3 minus 0.2x, enter, and then we'll differentiate this. So we go to math, 8x, vars, y vars, function, y1, x. Now for Windows settings, we're on the interval from 0 to 15. So x min is 0, x max is 15. We'll let the x scale stay 1. But I want to find where acceleration equals 0. That means I'm looking for the x-intercept for my acceleration function. So let's zoom in on the y-axis. Let's look at -1 to 2, and let's graph this. Okay, so I can see that I have an x-intercept on my acceleration function in the neighborhood of 2. So let's use equation solver. And we'll let our left bound be 1, our right bound be 3. So let's go to second trace, 0. We're going to find the 0. Now I'm on the velocity function, so we'll hit the up arrow key, and that puts us onto the acceleration function. And I need a left bound, that's going to be 1, and a right bound is going to be 3. And we press enter, and we have a root at 2.1516575. Okay, so we have that acceleration is equal to 0 at t is approximately 2.1516575. So when a of 2.152 equals 0, the velocity is constant, which means that it does not change. Next, they ask us in part B at time t equals 6, what is the velocity and acceleration? Is the particle speeding up or slowing down? So let's go back to the graph. So now I'm going to go to second trace into the calculate function, and we're looking for value this time. And so the x value that we're going to put in is 6. And so we see that at x equals 6, the velocity is 0.709571. So let's say v of 6 equals 0.709571. And what is the acceleration? Let's go back to the graph. And all I'm going to do is toggle to the other graph. And so we can see our y value is negative 0.148919. So negative 0.148919. Since signs are opposite at t equals 6, the particle is slowing down.